This person could be like driving into walls.
Right, or like suddenly stopping and starting. So,
Wait, should we draw the line?
you don't have to connect the dots. No.
Would it be wise?
Is that what you're trying to say? Like connect the dots? No, you don't have to.
Should we though?
I mean, so understand you're then making up stuff at that point because you don't know what's happening. Okay, so if it helps you, yes, but understand it won't necessarily be a nice smooth, connection. It might go up and down and up, and then to your point, so we don't know. That's just it. So that's a good question. All right. So obviously, when it comes to graphing, I know this, well, maybe it's not so obvious. Sometimes students, aren't sure, right? We normally graph on the x-axis time, right? Time is an independent variable, something that doesn't really, it changes, but we don't affect how it changes, right? It's not changed by something, it just kind of is. We think of it as being constant, even though, I'm sure other physicists and things would argue with that. But anyway.
Black hole and gravity.
That's right, exactly. So, we're going to look at that time in minutes. Okay, we're going to graph that time because the time is in minutes given to us here. And then we're also going to graph the velocity here in miles per hour. Something we want to keep in mind, right? Velocity is in miles per hour. We're talking, though, about time spent in minutes. So it's something we want to kind of keep an eye on there about that. So anyway. So let's see, the highest we have to go is 60. So I think counting by 5 should be good. So 5, 10. Okay. And then our time interval goes out to 60, so I guess we can kind of do the same. Okay. And then we'll plot our points. So let's see here. 0 is 26, so just a little bit higher. 10 is 40. 20 is 55, 30 is 10, 40 is 60, 50 is 32, yeah, they do bleed, yes, 60 is 45. If it bleeds, Ryan, if it bleeds, you can kill it, okay, just so you know that. All right, so you have these points. That's from like Predator, I think.
Yeah.
Predator.
Right.
If it bleeds, you can kill it. That's what Arnold, I think, says it or something like that. So again, just to highlight this, a couple people asked, but just to make sure you all got this, right? When we have coordinates like this, okay, our tendency is to want to connect these dots, right? That's what you guys did since elementary school. Before that, you want to connect the dots and make a nice little pretty picture. The problem is, though, we don't know what exactly is happening between these time intervals. We're going to assume it's continuous, but we don't even know that, all right? So we want to be very careful about any sort of assumption here. We don't know, from between this point and this point, I could go up to 70 miles per hour and then back down to 20 and then up to whatever it is, 40 there.
I've been driving for a terribly long amount of time, but I can tell you it would be very difficult for me to just increase, going from 26 miles an hour to 40 miles an hour over 10 minutes.
Ryan, you can get
a perfectly straight line.
Exactly. So how can it not be continuous? Well, I mean, we could we could hit a wall, and then we back out of that wall, and then we keep going somehow. That's a good question. But you're right, Donovan. Most likely it would be continuous. You're right. So what's that? Okay. So anyway, so we want to now take that data and we want to find the area under the curve after 40 minutes of driving using a right Riemann sum. Okay, so right Riemann sum, and we want to find the area after 40 minutes of driving. So that means we are not using all of our data here. We're only going from 0 to 40. All right, and it doesn't say how many rectangles to use here.
Well, wait, after 40 minutes of driving, wouldn't that be from 40 to 60?
find the area under the curve after 40 minutes of driving. So 40 minutes of driving would be from time 0 at 40 minutes later. I see what you're saying.
After driving for 40 minutes would be...
Yeah, after driving for 40 minutes, what would be maybe, or something like that, yeah. I don't know, yeah, even then. But, yeah, after, yeah.
Yeah.
Find the area under the curve after 40 minutes of driving. I think, yeah, after the first, well, I should even maybe put here.
I mean, honestly.
No, that's a good
purposes, it's irrelevant.
How about this? Find the area under the curve after the first 40 minutes of driving using the right Riemann sum. Okay? So that will then help us kind of know, okay, that's our first 40 minutes from 0 to 40 minutes. So we are not told how many rectangles to use here, so it's kind of up to us. All right, we actually have a lot of options. All right, well, not a lot of options. We really only have about 2, I would say. We can use 4 rectangles, or we could use 2 rectangles, or I guess we could use 1 rectangle, although that wouldn't be very exciting. So let's use 4 rectangles, because again, we know that the more rectangles we use, what's going to happen with our answer? It'll be probably more accurate, right? So that's our goal. So after the first 40 minutes. So for this first rectangle between 0 and 10, that's our first one, second one, third one, fourth one there. So rectangle 1, 2, 3, and 4. Okay, they're all going to have widths of 10, so that's going to be easy. And for that first rectangle, since we're using a right Riemann sum, what's going to be the height of that first rectangle?
40.
40. And then for the second rectangle?
55.
55 is the height at 20 minutes, that's right, okay. For the third rectangle, 10. And then for the fourth rectangle there, 60. So we get then 400, 550, 100, and 600. And if we add those all together, we get 1,650?
Yeah.
Now.
Wait, can you see the...
Oh, yeah, sorry.
Can you see what?
Ryan tested so much, like...
It's okay, my voice still does it too sometimes.
Wait, I didn't even do that. I didn't... My voice didn't even crack.
It didn't? It's okay, it happens. You're going through changes.
You're right, when a man loves a woman.
Okay.
Like I said, my voice still does it too when I get tired or something like that. So it happens. So this is the area under the curve, but there's actually more meaning to it. There's actually more meaning to it than we might expect. So we could just say, okay, this is area, so it's just like units squared. But each one of these axes actually has a meaning behind it, right? This is a time in minutes. This is a velocity in miles per hour. And what are we doing here to get the area of these rectangles? We're taking a time in minutes, so this is minutes times miles per hour. Minutes times miles per hour, minutes times miles per hour. Now, when you multiply minutes times miles per hour, your units are kind of funky because it's minutes and you're mixing it with per hour. So let's convert this. All right, if instead of saying 10 minutes, what else could we have said here? What is that as a hour? 1/6, right? So instead of saying 10 times 40, we could have said 1/6 times 40, 1/6 times 55, 1/6 times 10, 1/6 times 60. Okay. We could also multiply the whole thing by just by divide by 60. No, we have to divide by 60 is what we have to do. Divide that by 60. So anyway, if that's the case, we end up then with 6.667, 9.167, 1.667, and then 10. Which then we add those up, give us 27.501. And again, just to show you here, we could have easily just have taken that 1650 and divided by 60 to get the 27.5. I guess I have a rounding error there because of the 7s that I rounded to there. Okay. So again, I could have. So what I did here is instead of saying 10 minutes, 10 minutes, 10 minutes, 10 minutes, 10 minutes, and then mixing that with miles per hour, miles per hour, miles per hour, miles per hour, I changed the 10 minutes to 1/6 of an hour. 1/6 of an hour, because 10 minutes is 1/6. So this is in minutes. This is in hours. Okay. And the use of that is because now we're multiplying hours with miles per hour. So what did we do? We did hour times miles per hour. What's going to happen to those units?
Hours are going to cancel.
The hours cancel, and it's just 27.501 miles. So what does this mean? What is this meaning?
Logical sense.
Yeah, we know the distance. The car traveled 27.5 miles.
That is amazing.
Approximately, again, because we are approximating using the right Riemann sum. We can know that the car traveled approximately 27.5 miles using only information about its velocity, or speed, I guess, at certain time period, or certain times. Okay, so here, Emma, you can kind of see, here's a bit of an application that you were asking about yesterday. How's the area under the curve, Emma, going to be useful? So here it is. We ended up, by finding this area, we ended up doing time times miles per hour and yielding a change in position. Okay, so this is like a net, we call this the change in position there, so 27.5.
And that makes sense logically because if you go back,
If you integrate velocity, what do you end up with?
you get position.
Position. So it makes sense. It makes sense. We're very busy with important things, right, Emma? Yes. Okay. So we might need to, like, I know a teacher that institutes like a cell phone jail where she like takes people's cell phones and like puts them in a paper bag and like right on their desk and stuff like that. So I hope I don't have to do that, but you know. Anyway.
That takes a lot of patience.
So yes, I know. So all right. So 27.501 is the final answer there. All right. Flip it over here and go ahead and find the area of the curve after 40 minutes of your driving using a left Riemann sum. Okay, so go ahead and do the left Riemann sum. Okay, it's very similar. And let's do it with the 1/6 time intervals instead of the 10 minutes. You know what I mean? So 1/6 of an hour instead of 10 minutes for the time intervals. So again, it's after the first 40 minutes. First 40 minutes.
So after the first?
No, for the first 40 minutes. So from 0 to 40.
0 to 40.
Yep, 0 to 40. We did, but for a right Riemann sum. I want you to do a left Riemann sum. Now for
doing
left.
the 60? Oh, no.
Nope. First 40 minutes, but you're just using the left endpoints now instead of the right endpoints.
Now we just use 20 squares.
But again, use the 1/6 instead of the 10 for the time, because we'll use the 1/6, which is we'll keep it all in hours.
Zach, what did you do? Good. 31? 31? All right. Yeah. We can start the other one too, all right? Jack, what the hell's going on? Question? You? Sorry? Oh, yeah. So you don't do the one thing? Oh, great. No way. Keep telling me about that. It's 45. Okay, cool. You get to know that. Looks good. We're going to go also be doing the trapezoidal. But that's what it's really true. Is that kind of always Wow!
Minus 1,000.
My calculator, your own calculator? What's the calculator?
Did you truncate?
I didn't truncate. You truncated? I truncate. This is yours? No, mine. Oh, that's
Okay.
Is it mine?
So 21.834.
Is that really it?
Right? And again, what should the units for this be? Miles. Because what are we doing? We're taking the 1/6, which is in hours, times miles per hour. Miles per hour times hour is leaving just miles. So this means, okay, the car traveled approximately, I'll get you there, Donovan, 1 second, 21.834 miles from t equals 0 minutes to t equals 40 minutes. Okay? So there's kind of like a meaning there. All right. Donovan, question? Again, for me, it's you should be close, and the idea is that your numbers should kind of match up to what you add up to be there. So some people truncated; they were off by like a few decimal places from this because I round. So that's all. Yeah.
I just said
21.831. So did you truncate too?
I think I forgot to add an extra 3 to 4.3.
Okay, yeah. So make sure when you do that, you want 3 decimal places as be consistent with that 3 decimal places. Don't leave one off. Okay. All right. Great. Let's try this next one here then. Last one we're going to look at. We're going to do the the trapezoidal rule here, and it says to resketch it. So I'll just quickly I guess redraw it here. So. Yep, the same graph. Just to have it here because we already drew on the other one. So. Okay, and let's see here again. 0, 26, 10, 40. 20, 55, 30, 10. $40, 60, 50, 52. 60, 45. Okay. All right. And now we want to use the trapezoidal rule to approximate the distance traveled by the car for the hour. For the hour. So now we're no longer talking about the first 40 minutes. We're talking about the distance traveled by the car for the hour. All right. So how many trapezoids do you think we should use here?
One.
We could. But I think 6 would probably provide the most accurate, because that's as many as we can possibly do is 6, right? We can do basically all the subintervals that we were given here. We can't do any more than that. Well, that was, Connor, you know, that was very considerate of you, thank you. But also make sure you follow the directions too, because, you know, that's going to be more important. All right. Respect the curve, very good. All right. And again, maybe instead of having 10, 20, 30, 40, 50, 60, I could put like 1/6, 2/6, 3/6, 4/6 of an hour, right? Because if we put these kind of in terms of an hour, that might be helpful. So anyway, all right, so for our first trapezoid here, all right, so trapezoid 1, it's going to be equal to 1/2 times the base 1. What's our first base there? 26, plus our second base, 40, times the height, which is what, Tyler? What's the height of our trapezoid here? 1/6 or 10, whichever one you want to use. I'm going to use the 1/6 just to keep all the things in hours. So yes, very good. Okay, trapezoid 2. Okay, 1/2 times base 1 for this is 40, right? It's kind of nice because it uses the base 2 of the previous one, so it kind of helps with, you know, doing that. And then looks like at the next base 2 is going to be 55 times 1/6. And trapezoid 3 is 1/2 55 plus 10 times 1/6. And trapezoid 4 is 1/2 times 10 plus 60 times 1/6. Trapezoid 5 is 1/2 times 60 plus 32 times 1/6, and then finally trapezoid 6, 1/2 times 32 plus 45 times 1/6. Arithmetic it up. All right.
What is 1/6?
All right, so get 5.5 here for the first one. 0, 0. Do you want to put that there? If you don't put zeros, they'll understand it to be zeros, right? And then for the next one, we're going to do 40 and 55. So 7.917. And then 55 and 10. 5.417. Again, if you want to truncate, you can truncate too. That's fine. It'll be a slightly different answer. Oop.
No.
That's wildly different. You're double checking just like I did.
Yeah, because I feel like I had to add one because I missed. I put a 5 instead of a 6.417. I think I made a mistake. That's why. And I was trying to correct it.
38.
Yeah, I got 4.
Never mind.
Yeah.
There you go.
Also,
Fixed it. Did I make a mistake somewhere?
I did the interval of 10 and then just divided by 60 after.
Yep.
Final.
Yep, that's fine.
You go down in the blue.
Okay. So there it is. Again, that would be in miles.
That's wildly different.
Yes, it is pretty significantly different from those other ones there, right? But also understand, why is it different? Why is it so significantly different? Why is this one so different from the other two? Okay, so it's going to be more accurate. And we did 6 trapezoid, and yeah, it's a longer interval, don't forget, right? We were only going for the first 40 minutes, For the other two, this is for the entire 60 minutes, so it should be longer regardless, right? Because we're going further. So, all right, cool. So there's that. Any questions on that? That was just a little bit of practice there. All right, so let's go to the next one here. Now, the next one deals with, you can see the title there at the top is uneven interval widths. So, yeah, there's another one. Oh, what? You don't have yours?
No, I thought I just grabbed this graph on there.
Gotcha. All right. So if you guys would please, I could go make a copy for Emma, and then if you would please go ahead and graph. Okay, graph that. Poor favor.
Poor favor. We have the same ruler. Hey, we have the same ruler.
This is mine.
No. Yeah, so now you can working alone on a Tuesday night. I'm trying to kill myself. Why? Sucks. Why are there typically people alone on weekdays? They do on Tuesdays and Thursdays. Yeah, it's just a bunch of accidents when I come jump. So
Yeah. I gotta go pick that up now.
Zero down.
It's a 15. That doesn't even fit.
You gotta make it 15. You gotta do it with your mom last night.
Jesus.
Okay.
Hey, Emma, take this away to chair.
Yeah, do it.
Dude, that's a good idea. Switch them out.
I'm out positive.
Right now.
During the 10 seconds.
Why is that? I didn't do anything.
I guess I can't do that.
No, I don't want to write it. Emma, you should all this kind of shit. Hey, Mr. Wigg. Hey, how's it going?
That's going well.
That's good.
Good.
You talking like that on purpose?
What are you talking about? I always look like this. Friend Emma.
Emma.
Like, you have things in your head.
I don't know I do what?
They're making fun of you. I think they're juniors too. I mean, almost adults. Being a 17-year-old and teachers. They go down to the actually do launch like
Oh, no. No, I messed it up. Can I get another one of these?
Not right now.
Make copies.
Not right now.
That's what you get for using pens. Stupid. You alright there, Ryan?
It's gonna bother me so much.
What kind of noise was that? Scratch that. I don't want to know. That was disgusting.
Like, how badly is it messed up? Alright.
See, those two dots right there?
Yeah.
Those are wrong.
Just put X's through them then. It'll be fine.
It's not perfect.
I understand.
I like my notes to be pristine.
Okay. Cool. So the good thing about our units here, right, on the x-axis is time in seconds, and the rate of volume of water is in milliliters per second again. So this is nice. The units are not changed up on us. We can kind of keep our units. All right, so this is a table that shows the rate at which water is coming out of a faucet. Somehow they're able to measure the rate at which the water is leaking out of the faucet over different time periods. Okay. Right? That's I don't. Yeah, it's kind of like all right, we can do this, but why? Like, no, let's not fix it. Let's study it. You know, kind of thing.
It's odd.
Yes. Okay, so 0 is 8.
So those dots actually work out because they're just corners.
Perfect.
Where my Riemann
Yeah, see? You don't even know. Sometimes.
So we use left.
Wait, how much did you make? That's money, man. Yeah.
All right. So there's like the graph, right? Something like that. Again, we really should be hesitant here to kind of connect the dots, right? Or to kind of try and fill in between. True, but we want to be careful here because when we're given tables, we want to be very careful about trying to assume what's going on between those dots. Okay, we're not told it's continuous. We're not told the function here is continuous or anything like that, so we just got this. All right, so we're going to approximate the area under the curve after 10 seconds. So after these 10 seconds we got here, using a left Riemann sum, what is the meaning of the approximate area underneath this graph? So since, well, again, no rectangles, but how many rectangles can we do? So we can do 4. We can do 4 at most, right? And so that's what we'll do is we'll go with the 4.
Okay, this
all right.
is right.
So we'll say rectangle 1. All right. That first rectangle, what will its width be? Yeah, so this first rectangle width is 3 times, and then its height, since we're using a left Riemann sum, its height is 8. Okay, so the first rectangle width is 3, and then the left Riemann sum, so it's 8 is the height. For rectangle 2, that's the rectangle here, the kind of narrow rectangle here between 3 and 4. Okay, what is its width? The second rectangle. 1. That's right. And what will its height be? 12. Okay, again, left interval. The left-hand side of that interval is 3, and so its height is 12. And so again, we have one interval here, and then another interval here, and then from 3. Oops, sorry, I made a mistake here. This is all 1. And then here from 3 to 4, that's our second one. And then from 4 all the way up to 8. Okay, that's our third interval, and then from 8 to 10, that's our fourth interval there. So from all right, and so our third rectangle has a width of what? So 4 to 8 has a width of 4, right? 4. And then a height, left-hand sum there, 15. And then rectangle 4 has a width of 2 and a height of 11. So you get 24, 12, 60, and 22. So we get 8 and 5. So 58.
What?
Did I add that up incorrectly? Oh my gosh, yes I did, sorry. 8, 2, and so it's 5, and 118. I missed the 6. Okay, 118 what?
Milliliters per second squared.
Milliliters. Just milliliters.
Yeah, because seconds over 1.
It's milliliters per second times seconds, right? So these are all in seconds, times milliliters per second. So the seconds will cancel and leave it with just milliliters there. So 118 milliliters is what we'd expect. Okay, so we can say something like 118 milliliters of water. I should say approximately. And I ran out of space. Approximately 118 milliliters of water leaked out, okay, over the 10 seconds. Okay, that's our answer there. Approximately 118 milliliters of water leaked out over those 10 seconds. Question? What is the meaning of the approximate area underneath the graph? So yes. to answer that question, we need to give that little sentence there to describe it, okay? Absolutely. Okay, so I think for the remainder of class, yes, we're done. We're not going to move on from that. All right, for your homework, though, here's what I'd like you to do. If you flip it over, you'll see there's a C and a D. Okay, I want you to do that. And then in addition to those, so you're going to do, I'll just show you here, you're going to do C and D for homework. And then I also want you to do a trapezoidal rule approximation for f of x equals x times the tangent of x on the interval from 0 to pi over 4. Whoops. I want to include that pi over 4. And n equals 4. Anyone want to guess what I mean when I say n equals 4?
Number of
4 trapezoids. You got it. Okay? And then that's your third thing I want you to do. And then fourth thing, page 353, number 53.
Cool, Mr. Witt.
Parts A through BB.
What?
BB. So like it goes A, B, C, D up to Z, and then A, A, B, B. That's all those parts.
Are you serious?
Time to
No.
update my students.
That only happens in like concert rows, I feel like. You go like A, B, C, A through Z, and then it goes to A, A, B, B, Z, Z, C, C, D, D.